Hi everybody, welcome back to this channel. Today we're going to talk about the general circuit analysis in S-domain, which means we're going to cover the node voltage analysis and mesh current analysis and in several topics. So today probably it will take 5 video clips. The topics would include the node voltage analysis. I will start with the basic case that has the current source only or current sources only. And then we're gonna look at this in the second video clip. We're gonna look at the cases with the voltage source that contains the voltage source for the node voltage analysis. And for the mesh current analysis, there will be 2 video clips. The first one would be the base case that has the voltage source only or voltage sources only. There will be 3 different cases for how we deal with the current source for the mesh current analysis. And then the last video clip, the 5th video clip, I'm gonna show a couple of examples that have the dependent sources. If you remember, the current controlled voltage source, voltage controlled current source, so on and so forth. There are 4 different types of dependent sources. So I'm going a lot in much greater detail than the text did. Hopefully you will enjoy the videos. Let's start with the node voltage analysis, the basic case. And remember, what is the node voltage analysis? The node voltage analysis is basically we're writing the KCL equations at each node, right? And the KCL equation will follow the convention that all the current leaving from that node through the non-source element, they will add them together. That's going to be equal to the currents entering that node from the sources. The source, of course, is going to be the current source, because if you have voltage source, we don't really know what that current is, right? And the one thing I want to point out is that from the first exam, we just did the first exam, I noticed that some students didn't know the difference of voltage source and current source. I hope I will clarify here. I hope everybody should know. I mean, you're taking the circuit for such a long time, you couldn't distinguish from the current source. And the notation we use, this is the voltage source, right? So this is the independent voltage source, or this is the dependent voltage source. That this voltage source may be controlled by current or may be controlled by voltage, right? So these are voltage sources. And then we have the current sources. So this is the independent on the left, and we have the using a diamond with the arrow, that's the current sources. I hope I will not see this tragic situation. You don't really recognize the voltage and current source. And let's start with the basic case. The basic case, we have current source only. The reason why it's basic is because we are writing KCL equations, right? The current source, these are known quantities, so we can easily write the current, KCL at each node. So let's start with the node number 1. Let me maybe get this a little bit smaller so I can utilize the area here better. And so in this case, we start with the node number 1. And I'm assuming this is node number 1, and since I already labeled node number 2, node number 3. And if you are given a problem, the reference node. So this is the reference node, right? So this is the reference node. If the reference node is not labeled, you can choose your own, and then you label the node voltages and you start solving the problem. Since here I already give you the node voltage, the reference node labeled, we start with the node number 1. So the current leaving from the non-source elements, that's going to be, let's see, V1 S over 5 over S. That's the current leaving from the capacitance plus the leaving from the resistance, 3 ohm resistance, as V1 S minus V2 divided by 3. So I assume you already know the relationship between the element voltage and the node voltage. If you're still not sure about this, go back to the phasor, right? Go back to the phasor case. We had very detailed analysis on that. Basically, the simple KVL equation that so that should be equal to the current entering from the source, which is 2 over S, and node number 2, and we have the current. What happened here? So node number 2, I should close this. And node number 2, I have the current leaving from the 3 ohm resistance, that's V2 S minus V1 S divided by 3 plus V2 S divided by 2 plus V2 minus V3 divided by 3S. This is all the current. That's equal to the current entering that node from the source. There's no current source there. And node number 3, and that be equal to that's going to be the current leaving through this 3S, that's V3S minus V2 divided by 3S plus V3S over 4. That's equal to the current entering that node. Entering that node should be negative S over negative 2 over S, because 2 over S is the current leaving from node number 3, right? So therefore negative that current would be entering current from that source. And you can put the, you can factor this the coefficient in. So we have 5 over S and plus 1 over 3. No, 1 over 5 over S, 1 over 5 over S, plus 1 over 3, and times V1S, and minus the first equation. I'm trying to collect the terms, and minus 1 over 3 times V2S, that's equal 2 over S. For the second term here, I have negative 1 over 3 V1S, and for V2S plus V2S, I have 1 over 3, right? Plus 1 over 2, plus 1 over 3S. That's V2S, and minus 1 over 3, 1 over 3S times V3S. That's equal 0. And for the last one here, if I collect the terms, that should be negative 1 over, for the first one, actually 0, right? I don't really have anything for V1. So for V2, I have a negative 1 over 3S times the V2S, V3S, let me see. Yeah, that's V2S. The V2S and plus 1 over 3S plus 1 over 4 and V3S equal to negative 2 over S. And since some of you asked me to really work to the very end, so I'm gonna take a little bit longer time to work to the end. Or you can formulate this into the matrix form. In matrix form, we would have the 3 by 3 matrix, right? So in this case, the first element here, we have 1 over 5 over S plus 1 over 3. And the second element here would be negative 1 over 3. And the third element for this is going to be 0. So, and this times V1. These are the unknowns, right? V1, V2, and V3. And on the right-hand side of this equation, it's going to be the knowns. And this is the current sources. In the first case, I have a 2 over S. And for the second equation here, I have a negative 1 over 3 for the first element. For the second element, I have 1 over 3 plus 1 over 2 plus 1 over 3S. And for the last element, I have a negative 1 over 3s. You see this is negative 1 over 3s. And for the last element here, for the last row here, on the right hand side, and this is 0, right? For the last one here, I have 0 for the coefficient of v1 because we don't have anything there. For the v2s, the coefficient is negative 1 over 3s. And for the last one, the coefficient in front of v sub 3s, which is 1 over 3s plus 1 over 4. And the equation here, the source on the right hand side is negative v2. And if you observe this, if you observe this with the circuit we have, let me copy that circuit here. So if you compare this with the circuit you have, the matrix form, and what you have here is at each diagonal elements, right? That's just the sum of the admittances, right? So at the 1 position, that's the admittances associated with the node 1, right? I have 1 over 3 plus 1 over 5s. And at the node number 2, that's the 2 position, and that's I have 3 admittances, the inverse of each of the 3 impedances. The inverse of each is an admittance. So that's the sum of the admittances connecting at node 2, and so on and so forth. So in the end, the off-diagonal elements, let's see between this 1, 2 position, right? The first row and second column, that's the impedance, that's the admittance between node 1 and node 2. But we put negative sign there because the convention we are following. And so therefore you can write the equation by inspection. Okay, so you don't if you only have a current source, right? So this is the basic case you can do, just to write the equation by inspection. In this case, for here we'll get a 0 because from Z1 and Z2 there are no passive components there. So no resistor, no capacitor, no inductance. So therefore the admittance will be 0, right? And on the right hand side, this is the current sources. Okay, so we're gonna look at a few examples, the 3 cases with the voltage source. If you have voltage source for the node voltage analysis, is a little bit different story. We're going to take a look at that in a moment.